Hello, here we go. We're going to talk about graphing rational functions, and right there on the screen you see y equals 1 over x. This is one of our parent functions from the very beginning of the school year, and it looks like this. It has an asymptote right down the center on the y-axis. It has an asymptote horizontally on the x-axis there. And then the graph has one curve over on this side and one curve over on that side. And we have sketched these before, but these functions have a unique domain and range to them. If you ask somebody the domain, well, it does go to the left forever, and it does go to the right forever, but in the center there is a gap. Now, we haven't had to use this notation in a while, but it doesn't mean we haven't talked about it. Wherever you use this unified or the U symbol, it means there's a break in the graph. And in this one, it's where the asymptote happens to be. Remember, domain is talking about sideways motion, so on this particular function, the break is right at the middle at the y-axis. And similar, if you were to write the range out for this one, there happens to be a break in the middle, but this is talking about the bottom toward the top of the function. So the break this time would be right here in the middle. Either way, we can state the domain and range for these type of functions. Now, we haven't graphed these in a long time, but now we're going to start getting back into them because, as you can see, there's a variable in the bottom that makes this a rational function. So let's look at these next couple. I made up a couple to kind of remind us that we have done this. And every graph follows the same rules of motion. So here, I would say the number next to x, whether or not they put it in parentheses, you can, but the number next to x, remember, is sideways motion. You set it equal to 0 in your head, and so you'd go left 2 units. But since this is a rational function, that means there's an asymptote right there, left 2 units. And then on the other one, you would have to go 1, 2, 3 vertical units, because up-down motion is still present in this. And I'd have another asymptote, this one cutting across right there. And once again, since it's a rational function, it's going to have a certain look to it. It's going to go like this. And I could say, hey, I know what the domain of that function is. The domain of that function is negative infinity. But now going sideways, where is the break in the action? Well, the break in the action's at negative 2. That's where that vertical asymptote is. And then I'd pick up the same graphing technique on the other side of the asymptote. Range. Once again, negative infinity, but where is the break in the action? It's at positive 3, and that's where I would pick up the rest of the graphing, and I have a domain and range for that function. Now, I mentioned this, we haven't done domain and range in a while, but you're going to be doing some problems out of the book. And one of the things they're going to have us do is give us a quick sketch. Remember, I'm not making a table of values. I'm just doing a quick sketch of this. And then they ask me to describe the transformation of the graph. When they say, I just want you to tell me what the domain and the range are. And that's this part of the answer. When you look at the answer key, you'll see what I mean. Anyway, let's take a look at my next example. Once again, this part down here at the bottom, I'm putting it in parentheses. That's the part connected to the x. And if I set that equal to 0 in my head, that would mean I'm going 1 unit to the right, which will give me an asymptote right there. This part of the puzzle is going to shift me down 4 units, which means I have another asymptote right there. And if I was going to sketch the graph of this one, well, normally I would just follow the same pattern I've been doing, la la la, and I didn't make that really dark because I'm going to erase it right now. Don't forget, we have things called flips in here. We are going to reflect this thing over the horizontal asymptote. So instead of looking just like every other graph, this one is going to go up on this side and down on this side. And domain. Well, it's still going to go negative forever, and it still has a break in the action at 1. I would have to pick up my pen to continue on to draw the rest of that graph. I'm going to get rid of that little arrow there. It's in my way. And that would be my domain. And likewise, my range, well, my range goes down forever, but there is a break at -4. That's where I'd have to pick up my pencil if I was going to graph the second side of that graph. So, just a little reminder, we have done this, we just haven't done it for a while, but little reminder, that's what we're doing. Now, I have to show you something that I haven't talked about yet, and it has to do with the numerator here. That's one of the things. And then there's a little bit more coming our way, but here we go. I actually made up an example where the top number here is a 5. And what happens is, if I graph this on my graphing calculator, it's not going to write in the asymptotes for me. Down here below in the function, I put it in parentheses. That's at -2. Technically, there is an asymptote. I'm drawing right on the graphing calculator display. There's an asymptote at -2, but you don't see that. The calculator doesn't do that for you. Also, this guy right here would be at -3. And that would put an asymptote cutting across through at -3. But what about that 5? Well, here's the thing. We are still sketching graphs. We're not making tables of values. Also, this is just my graphing calculator drawing the picture for me. But what I wanted you to see is, what is the difference if that top number is something like 5 compared to like a number like 1. So let's take a look. Here's the big difference between the two graphs. Once again, my calculator will not draw in the asymptotes for me. It's not going to do this part. I'm the only one who knows how to do that. Calculator's just a machine. But what I wanted you to see is the difference between the 5 in the numerator and our good old-fashioned 1 is the distance our graph is from the middle. See, when we shift one of these rational functions, it's like taking the origin and relocating it. But you'll see the blue graph is definitely, and I'm drawing on the calculator graph down here in case you don't see me, I'm drawing right here. The blue graph is pulled farther away from that pivot point, that central location. The bigger the numerator number becomes, the bigger this number gets, I'm right up here in the numerator, the farther that's going to pull away. Now, the thing is I am never going to ask you exactly how far it does pull away from there. But I do expect you to understand that that's just like any other part of our graphing system that we've been talking about. Larger numbers are going to amplify what the graph looks like. So here we go. I need to get you guys to look at something like this. Now see this one? The top number's 25. That's a big number. But this thing still has an asymptote at 1, right? That's a vertical asymptote at 1. So if I sketch that in, and then it has a horizontal asymptote at 2. So if I sketch in the horizontal asymptote at 2, that would make this like my new origin for this graph. Well, look at how far that got pulled away from the thing. The larger this number is, the farther it's going to get pulled away from its central location. Now, if this number wasn't 25, if it happened to be a 1, I'd have a graph that would be coming closer. See, I'm sketching it in by hand on top of this. But I would see this, something that is closer to that origin. I'm going to get rid of that graph now because I just wanted to give you a visual clue. But the bigger that number gets on the top, whoops, I don't know what I just did. Okay. The bigger that number gets, the farther it pulls out. But it still has the exact same type of relationship. In fact, this blue graph, it's very hard to see what's happening because it takes this one, since it's been amplified, it's going to have to cruise out way over here till it starts to become asymptotic. And it would have to go quite a bit up before it becomes asymptotic to my, whoops, sorry, I'm trying to get a black pen, oops, as I try to get close to these, okay? So what does that mean? Even though this number is big, it doesn't mean anything when it comes to the domain and range here. I would still have a domain and range that represents where my two asymptotes are. One of my asymptotes is at 1. That's going to affect the domain. One of my asymptotes is at 2. That's going to affect the range. In fact, I'm going to tell you, on the test, I'm not even going to have you guys draw a picture for me. I'm going to ask you about the domain and range. I'm going to ask you, well, wait a minute, what's with this one? This one isn't even like what we call HK form. See, all of these problems I've been doing for you are in HK form. And then I give you this. Well, here's the topic. We haven't seen this yet. It's not difficult to do, but it does kind of tie a lot of the little pieces that we've talked about this whole school year together. This function that I'm looking at, y equals 2x minus 3 over x plus 1. Well, guess what? That means I am going to take 2x minus 3, and I am going to divide it by x plus 1. This was when we did polynomial long division. So I'm going to ask myself, what would I have to multiply this by to get 2x? And the answer is 2. So I'd say 2 times x, I get 2x. 2 times 1, I get 2. And then I don't know if you guys remember this trick, then I would subtract. And if I subtract, it hits both pieces of the puzzle. This would cancel. I'd get -3 plus a -2. That's -5. Now, what would I do with all this information? Well, here's what it looks like when I rewrite it. I would say, instead of this, I would say y equals -5 over x plus 1 plus 2. Remember, whatever the remainder is, we'd write it over the divisor, and we can express this type of problem in what's called HK form. If you look in our book, the book writes it like this. F of x equals some number we don't know, but it's a number that could amplify our graph. So they use A, and then they say x minus h plus k. So there's some shift going on sideways, and there's some other vertical shift over here. Well, guess what? We know how to graph this. So on the test, I would expect that you could tell me the domain and range for this thing. Well, if I wanted to do the domain and range, it's always easiest to look at its picture. So I'm going to say this has a vertical asymptote at -1, because I set that piece of the puzzle equal to 0 in my head. Whatever this thing says is my vertical shift, so I'm going to go up 2. I have a horizontal asymptote there. Normally, my graph goes down over here and up over here, but I've been flipped. So I'm going to get rid of those guys, and I'm going to say, you know what, let's use a different color. On this side of the picture, it's going to go up. And on this side of the picture, it's going to go down. Now, the thing is, the number here happens to be a 5. What does that do? Well, if I didn't have a 5 there, let's suppose I had a 1 there instead, like a -1, then my graph would have been closer to that origin point there. That'd be the only difference. Keep in mind, what am I going to ask you on the test? I'm going to ask you to possibly convert into this format, then tell me the domain and range. So let me get rid of the blue graph. I'm going to just undo that, get rid of the blue information. And I'm going to go back to the red pen since my graph is in red, and I'm going to do the domain. And I'm going to say domain. Oh, well, negative infinity. There's a break in the action at -1. Pick up the action on the other side of that asymptote and go forever. The range for this answer, well, negative infinity, because it goes down forever. But if I was to draw this picture, I'd have to pick up my pen at 2 and put my pen back down on the other side of the asymptote to continue forever. And that's what you should be able to pull away from this lesson. Now, I went through that like, boom, here it is, and I tied a bunch of pieces of information together. So let's go back, let's try another one. So here we go. I have another example right here. In this example, I'm going to convert it into HK form. How do I do that? I do it like a long division. So I'm going to do 4x minus 1. I'm going to divide it by x minus 2. What would I have to multiply x by to get 4x? Well, I'd have to multiply it by a 4. 4 times that would be 4x. But don't forget, I got to multiply by this guy too. So I'd get that. And then whenever I do long division, I like to use 2 colors because now I'm going to subtract. And that means that guy changes sign, that guy changes sign. That's going to get eliminated. And I end up with -1 plus 8, that is 7. Whoops, hang on. That is 7. There it is. So, how do we take this? Well, it is remainder over divisor plus, there's my quotient. That's what I had. So I've converted this original function, which, by the way, I should have said y equals or something. I didn't. Oops. Don't tell the teacher. Anyway, y equals 7 over x minus 2 plus 4. I have a horizontal shift. I have a vertical shift. This has been amplified, but it has not been flipped. This thing is not going to get reflected top to bottom. It's not negative. But if I wanted to tell you the domain and range, which, by the way, on the test, I would ask you, hey, could you tell me the domain and range of this function now that you've converted it? Hopefully you would say, sure. I'm going to go 2 units to the right. I'm going to go up 4 units. And then I say, well, that number is a 7. That's a big number, but, you know, what does it mean? Well, mentally, all it means to me is when I sketch this graph, I'm going to kind of be on the wide side from this pivot point. I'm not going to be real close to it. If it was 70, let's say, then it would be way out here, way away from it. But one thing I know for sure, it would still, I'm going to get rid of those big swoops, it would still have the same domain and range. Because the domain, well, it's going to go negative infinity, it's going to hit that vertical asymptote at 2. Then on the other side of that asymptote, I pick up the graph. Range, it goes down forever, surely it does. It goes up forever, but it has a break in the action on this one at 4. So for this particular graph, that's what I would have. I'm going to get rid of this little 0 here because it was not there. All right. So hopefully you got the rhythm of this and it's not too confusing and you go, oh, what about this one? Well, this time I have a negative 3x plus 4 in the top. Is that going to scare me? Heck no. I also forgot to do this, so I'm going to put like f of x equals that. So here we go. Maybe you want to pause this one, try it out, see if you could get the correct sketch or the correct equation, and then find the domain and range of it. Pause it and try it, and then hit play and see if you're correct. Okay, I assume you did that, so you just hit play, and you're waiting to see if your answer is correct. So let's go through it. I'm going to take that divided by that. I'm going to say I need a -3 up there. -3 times that is -3x. Then minus times minus would be plus 15. But wait a second. I'm going to now subtract this information, which means change all these signs. And I'm going to end up with a grand total over here of -11. So my new function, after I've rewritten it in HK form, looks like this. -11 over x minus 5 minus 3. So now I'm going to say, hey, if I wanted to know the domain and range of this, it sure would be nice if I had a graph to compare it to. So I'm going to just quickly sketch this graph that has a vertical asymptote at 5. It has a horizontal asymptote at -3. And then I could say to myself, this graph has been flipped over and it's been amplified by 11. So when I sketch this graph, let's use green. We haven't done that. It's going to look like this. It's going to be over here and over here. I could still tell you the domain and range. So when it says in the book, because these problems you're going to do come out of the book, when it says in the book to describe the transformation of the graph, you'll see it. I want you to just tell me the domain and the range. Because the transformation they're talking about means you don't have asymptotes in the middle anymore like you do on the parent function. Your graph has been shifted. So I'm going to say I am shifted 5 units to the right, which means I'm going to have an asymptote right there, which means I have a break in the action in my graph. Same thing goes with the range. Where's the break in the action? It's at -3. And away we go. There we go. Hey, I got one last trick up my sleeve. I do. Look at this one. What do you do if there's just a single letter down there? What if there's just an X? Well, you can do it the same way we just did. You could do, I'm going to divide 6x plus 7, but I'm going to divide it by x plus nothing. You can do it that way. It'll work. It'll totally work. What would I have to multiply this by to get this? I could do it. I totally could. But I want to show you, there's a shortcut way to do this one. Here's my answer instead. I say, hey, I want to convert this. I'm going to do 7 over x plus 6. How did I do that so quick? Well, I can rewrite this so it looks like this. See, they both have the same denominator, and it's a monomial. There's only one thing there. So if I separate it into 2 pieces, then I could just cancel the x's, and then I get 7 over x. I surely do. Hey, what does that graph look like? Oh, come on. Really? I made it this whole way, and you're going to... There we go. What does this graph look like? Well, let's do, hey, purple, what the heck? I don't go sideways. There is no sideways motion here. There's no sideways motion. So I have a vertical asymptote right on the y-axis, right down the middle. This graph goes 1, 2, 3, 4, 5, 6 units up. There's that asymptote. And then I would have no flips, little bit of amplification because it's a 7. And I would have this. So here's the thing I want you to get used to. If this number was 7, 17, 170, whatever it is, all it's going to do is it's going to cause this graph to pull away from its little origin point. If you know that's the only effect it has, it doesn't change where your asymptotes are or anything like that. It means you could still easily tell me that the domain and the range of this function is based on your idea of shifting this graph sideways or up and down. And there you go. So that is the lesson about this stuff. That's it. You can get the assignment out of the book, or I did take a picture of the problems from the book and I posted it on Canvas for you so you could get that done. Anyway, that's all there is to the graphing rationals section. Really, I'm not looking for the major graphs on the test. What I'm really concerned about is, do you understand the concept of converting this into the other format? Like, can you convert this into this? And based on that, could you still understand what the domain and the range is? If I gave you this, if I gave you this, could you convert it to this and tell me the domain and range? That's what I'm really concerned with. Sketching a graph, like a quick sketch of the graph. None of these are perfect graphs. Just a quick sketch helps you do that, though. So you might want to keep that in mind when you're doing this. And do remember, you can check stuff on your calculator, but I warn you, your calculator can't draw a huge graph. If it gets so pulled away from the center, it might be off the screen. So it does not hurt to have a good estimation skill on this. Okay, that is the end of the rational functions lesson. Have a good day.